On paper, the Bulletin looked routine. A camshaft gear, 60 thousandths of an inch thicker than the one it replaced. One revision to a part most owners had never seen and never needed to think about. Then came the compliance window. 100 hours. Bonanza, barren. Cirrus SR22, Continental-powered Mooney. If your aircraft ran a Continental IO-470, IO-520, or IO-550 built before August 2005, you were on that list. The engineers at Continental Motors had known this gear was undersized since 2005 and had been installing the corrected version in their own factory engines since that year. The fix was not in the old engines, and now, in March 2017, Continental wanted it there immediately. The cost, per engine, a minimum of $16,200. The number of documented failures that justified the demand, 13. Across 26,000 engines in the field, one failure per approximately 7 million flight hours. That is not a safety bulletin. That is a business model wearing a service bulletin's clothing. But the camshaft gear is the visible edge of a deeper problem. The real failure goes back 50 years into the architecture of the engine itself. It is not a defective batch, not a quality control failure. The cam sits above the oil line. Every shutdown, the oil drains off it. That is the condition. That is physics. And it is still there, inside your aircraft right now. I have cracked open enough of these cases to tell you what the filter says before the crankcase does. Stay with me. Are you flying your flat engine on the weekly schedule, or is the cam already telling a story you have not read yet? Subscribe to Sky Ranch and keep watching. You need to hear the rest of this. Get your eyes down on the crankcase layout and you will see the first problem immediately. The Lycoming camshaft sits above the crankshaft, at the very top of the crankcase, just under the engine's backbone. There are no pressurized oil ports aimed at the cam lobes, no dedicated circuit keeping that surface wet. The cam runs on splash lubrication only, oil thrown off the crankshaft and connecting rods as the engine spins. The moment that the crankshaft stops spinning, the oil film on the cam surface begins to drain. The Continental cam sits lower, below the crankshaft, above the oil sump. A mechanic performing preservation procedures can physically drip oil onto a Continental cam lobe using the oil drain port. On a Lycoming, the same approach cannot reach the cam at all. The geography is different. The drainage problem is not. Now look at the surface the cam relies on to survive. The hardening process is called carburization. Lycoming bakes the raw cam in a specialized furnace with carbon monoxide gas under heat, forcing carbon deep into the steel surface and driving up its hardness. The result is a shell 15 thousandths of an inch deep. That is 0.015 inches. Thinner than the phosphor bronze liner on a worn bearing. Thinner than 5 sheets of standard printing paper stacked together. That shell is the only barrier between the cam lobe and catastrophic wear. When the engine shuts down, oil drains off the cam first. It is the highest point in the lubrication geometry. Gravity does not negotiate with engineering drawings. Humid air enters through the cowl openings at the top of the engine. Through the day and night, the temperature cycles. When the cam surface cools below the dew point of the air trapped inside the crankcase, moisture drops out directly onto bare steel. In a high-humidity coastal environment, corrosion can begin in under 2 weeks. In a standard mid-latitude spring hangar, the threshold sits between 30 and 90 days. Corrosion on a cam surface is not surface rust you can wipe off. It is pitting, rust eating through the hardened shell from above. Each pit is a crater in the only 15 thousandths of an inch the cam has to give. There is no depth beneath it worth having. Once the shell is compromised, the underlying steel is soft and the failure accelerates. The first cold start after extended storage compounds every day of inactivity at once. When a stored engine fires for the first time, it takes several full crankshaft revolutions before oil pressure climbs enough to begin reaching the cam lobes through splash. In those seconds, corroded lobes run metal against lifter faces with no film between them. The hardened shell was 15/1000ths of an inch to begin with. Rust has already eaten into it. Now, friction finishes the job. Pitting becomes spalling. The cam lobe surface fractures and sheds material. What you see on a spalled lobe under a bench light looks like a lunar landscape. Craters, ridges, surface that was once glass smooth is now broken terrain. The lifter face that rode against it looks the same. Two components that were machined to tolerances of thousandths of an inch are now making contact across a fractured field. That material does not stay on the cam. It is ferrous metal, iron attracted to a magnet. It flows through the oil galleries, through the connecting rod bearings, through the main bearings, and into the filter. A mechanic who rinses the filter media in solvent and draws a pencil magnet through the collected debris will find it, black fuzzy material clinging to the magnet. That is cam material. That is early spalling with a message. Many owners never ask what the filter says between annuals. The filter is the most accessible diagnostic instrument in the engine, and the one most of the fleet is not reading. Early spalling takes 200 to 300 hours to produce particles large enough to appear obvious on the filter. The failure starts invisible. It arrives expensive. The Radial engine does not write this story. In a Radial, the cam is not a shaft mounted above the oil line. It is a ring, a single steel plate concentric with the crankshaft, driven at a reduced speed through a planetary gear. In a 9-cylinder Radial, like the Pratt & Whitney R985, that cam ring sits at the center of the engine's oil system, not at the top of it. 4 lobes on a single ring serve all 9 cylinders. When the engine stops, the cam ring does not drain to bare steel the way a longitudinal shaft above the oil sump does. The position that made the Radial a wide barn door for drag turned out, accidentally, to place its cam geometry inside the oil system rather than above it. The Radial also runs solid lifters, not hydraulic. There is no internal plunger dependent on oil pressure to maintain valve clearance, no hydraulic unit that drains during storage and loses its geometry on the first cold start. The architecture is simpler at the cam interface, and the failure mode that simplicity sidesteps is not trivial. The Radial was not designed to avoid this problem. It avoided the problem because it was built around a different shape. That is the difference between an engineering solution and an architectural accident. The flat engine inherited a vulnerability the moment the market chose efficiency over geometry. The Radial escaped it without trying. The cam runs on borrowed time from the moment you shut down. Stop the crank. The film drains. The clock starts. Here are the numbers that put a scale on that clock. The corrosion threshold is 30 to 90 days for a standard hangar environment. In high humidity, Cessna's own storage procedure documentation records pitting on engine cylinder walls in under 2 days for engines with fewer than 50 hours of service. 50 hours since overhaul, 2 days of exposure. That is how unforgiving the chemistry is when the surface hardening is not yet conditioned with operational oil deposits. The hardened surface layer on a Lycoming or Continental cam lobe measures 0.015 inches. That is not an estimate. That is the published specification. Aviation Consumers Survey of camshafts arriving at overhaul shops found that approximately 30% showed wear or loss of cam profile by the time they reached the teardown bench. 3 in 10 engines that made it to overhaul did so with a cam that was already compromised, not failed, not seized, but running on a diminishing surface that the owner had no reason to know about. The FAA General Aviation Activity Survey for 2020 puts the average fixed-wing piston aircraft at 95 flight hours per year. That is 1.8 hours per week. The manufacturer threshold for corrosion prevention is at least 1 hour per week, with oil reaching 180 degrees Fahrenheit. The temperature at which accumulated moisture vaporizes and exits through the crankcase breather. The average general aviation owner is not meeting that threshold most weeks. The average general aviation owner has probably never been told the threshold exists. The manufacturers documented this condition decades before most current owners bought their aircraft. The paper trail goes back to 1976. The Lycoming O320 H2AD entered production in 1976. It was installed in the Cessna 172, the most produced American general aviation aircraft in history, the airplane that has taught more Americans to fly than any other machine built before or since. Within the first production years, mechanics were finding cam and tappet spalling in new engines. Lobe faces were fracturing on aircraft with 200 hours in the logbook. Metal was appearing in oil filters of aircraft whose owners had never missed an oil change interval. By April 1978, Lycoming issued a series of modifications. To bring an affected engine to current specification required replacing the crankcase, the camshaft, and the tappets simultaneously. All three components. The engine that powered the airplane that taught America to fly had a documented cam failure problem in its first production year. Some of those original configuration engines are still flying today. Ask specifically which configuration you are purchasing before you sign anything. Greg Merrill, owner of Aircraft Specialties, ran the failure down to the electron microscope level. His shop analyzed cam and tappet failures from multiple engines, scanning for metallurgical defect, a wrong alloy, improper heat treatment, a bad foundry run. The equipment that reads metal at the molecular level found no smoking gun in the steel chemistry. The conclusion was that the chemistry in the metal is generally fine. The steel is correct. What kills the cam is corrosion. The architecture positioned the KM in a location where moisture and oil starvation can reach it before anything else in the engine. That is the root. Continental's version of this failure came faster and with more institutional fingerprints on it. In June 2009, Continental's outside hydraulic lifter supplier changed its casting foundry. The new part numbers 657913, 65795, and 65796 shipped into the fleet that summer. By November 2009, rapid wear was being documented in engines with fewer than 5 hours on the affected lifters. 5 hours from installation to a safety of flight concern. Continental issued Mandatory Service Bulletin MSB 09-8A on December 4, 2009. The language was direct: loss of engine power and a potential safety of flight issue can result. The Federal Aviation Administration issued Airworthiness Directive 2010-11-04, effective June 16, 2010. The compliance instruction was before further flight, not at the next annual, before the next departure. Lycoming is still issuing mandatory bulletins on internal component failures. Federal Aviation Administration Airworthiness Directive 2024-21-02, issued October 31, 2024, requires enhanced connecting rod bushing inspection at every oil change after reports of uncontained engine failures and in-flight shutdowns. Lycoming's own published content calls its engine noted for camshaft and tappet body failures, linked to the camshaft's position hindering oil distribution. That sentence is on Lycoming's website. About their own engine. In 50 years, the architecture has not changed. By the time mechanics had this on the table, the OEM had already decided what to do with it. That decision is why you are watching this video right now. March 29, 2017. Continental issues MSB 05-8B. The subject is the camshaft gear, 60 thousandths of an inch undersized. The history is this. Continental had corrected this in their own factory engines 12 years earlier, in 2005. Field overhaul shops were not required to install the updated gear until 2009. Engines rebuilt between those years in the field may still carry the old part. The compliance window in the original bulletin was within 100 hours of operation, or at the next overhaul not to exceed 12 years since last rebuild, or whenever the gear is accessible, whichever comes first. On a fleet averaging 95 hours per year, 100 hours means tear your engine down before the end of this year. The cost breakdown per aircraft was engine removal and reinstallation. approximately $5,000. Teardown and inspection, approximately $10,000. The replacement gear itself, $1,200. Total per engine, before any hidden discoveries, $16,200. Before any crack found in the crankcase. Before any bearing that comes out of limits on the bench. Before any cylinder that fails inspection. $16,200 is the floor. Continental simultaneously asked the FAA to issue an airworthiness directive, mandating this compliance across the entire affected fleet. The documented failure count was 13 confirmed gear failures across 26,000 engines, 1 documented forced landing. That number and that demand have been sitting in the same room for 8 years. Which part of that equation is the safety concern, and which part looks like something else? Drop your read on it below. The owner community produced the response any institution fears: organized, documented, and economically literate. AOPA ran the failure rate math publicly. Owner groups coordinated the response. The FAA declined to issue the AD that Continental had requested. By April 2017, Continental revised its position. MSB05-8B was demoted to CSB05-8C. The mandatory teardown and gear replacement became a visual inspection procedure requiring approximately 1 hour. Same gear, same engine, different bulletin. The bulletin changed, the architecture did not. The cam still sits where it always sat. The oil still drains where it always drained. Lay the two designs next to each other, and the verdict is in the geometry. The flat engine cam is a steel shaft mounted above the oil line, dependent on splash lubrication, with a hardened surface 15/1000ths of an inch deep, exposed to gravity drainage at every shutdown for the entire operational life of the aircraft. The radial cam ring is a circular steel plate concentric with the crankshaft, immersed in the center of the oil system, driven through a gear reduction, using solid lifters with no hydraulic unit to drain or collapse. Store both in the same humid hangar for 60 days. On the flat engine, the cam surface is dry from day 1. Pitting is possible inside 30 days. By day 60, the condition is compounding, and the owner has no instrument to detect it short of pulling a cylinder or threading a bore scope through the oil drain port. The radial cam ring does not produce the same drainage condition. The architecture absorbs what the flat engine cannot escape. The standalone cam repair, crankcase split, parts, and labor runs approximately $10,000 as a starting point. Discover the cam condition during a forced overhaul, and the cost rises to $25,000 to $45,000 for a 4-cylinder engine. The Lycoming factory. Rebuild runs $70,000 to $85,000 plus your core. That is the bill for an engine that waited in a humid hangar. The radial's cam is a ring at the center of the oil system. The flat engine's cam is a shaft sitting above it. That gap, measured in inches, is the gap between a $0 repair and a $45,000 repair. Whether the OEM's management of this condition over 50 years is an engineering constraint accepted in service of the market, or a documented failure mode maintained in service of parts revenue, this video will not answer for you. The evidence is in the record. Read Lycoming's recommendation that owners purchase only new cams at overhaul rather than regrind the old ones. Read Continental's mandatory bulletin demanding $16,000 per engine and then retreating when it costs them credibility. Draw your own verdict. Efficiency wins the market. The cam pays for it. The radial did not hide its weaknesses. A cylinder ran hot. You could see it, smell it, fix it on a muddy English field with a chain hoist and a set of banged-up wrenches. A Pratt & Whitney R985 that had taken shrapnel through 2 cylinders and lost half its oil pressure over France would still drag a pilot back across the channel. Its failures were external, visible, survivable. The flat engine moved the primary failure inside the crankcase. The only window into it is a 5.5mm flexible bore scope worked through the oil drain port to visualize the rearmost 3 cam lobes, 3 of 8 on a 4-cylinder engine. The failure hides until it does not. The mechanic who knows what to look for does 4 things. Most owners do none of them. Cut the oil filter at every oil change. Rinse the media in solvent, pour the contents through a clean rag, and draw a pencil magnet through the debris. Black fuzzy material that adheres to the magnet is ferrous particulate. That is cam material. That finding does not wait for the annual inspection. It waits for one phone call to the shop. Fly at minimum once per week, 1 continuous hour, with oil reaching 180 degrees Fahrenheit. That temperature is the threshold at which accumulated moisture in the crankcase vaporizes and exits through the breather. Below that temperature, the moisture stays and the chemistry continues. If that schedule is not realistic for how you own an aircraft, CamGuard is a documented corrosion-inhibiting oil additive with published test data behind it. It narrows the window, it does not close it. When you are buying a used flat-engine aircraft, low-time engine hours are meaningless without flight frequency records. A 400-hour engine that flew 20 hours per year for 20 years is not the same machine as a 400-hour engine that flew 100 hours per year for 4 years. The logbook hours are identical. The cam histories are not. Ask the seller for flight frequency. If they cannot produce it, that information has a dollar value in your offer. Ask your A&P to attempt a cam inspection via the oil drain port before you close on any flat engine aircraft. A flexible borescope, 5.5 mm or smaller, can be worked through the crankcase slots to the rearmost 3 cam lobes. 3 lobes is not the full picture. 3 lobes is better than no picture at all. Pitting on those 3 lobes tells you about the other 5. If this is the kind of forensic work that keeps you in the air, subscribe to Sky Ranch. Is your flat engine on the weekly schedule, or is the cam already writing a bill you have not read yet? Tell me below.